In every single Bitcoin transaction, there's this little 32-bit number that most people just ignore. But it has a fascinating story. It was abandoned, then brought back from the dead, and even given a secret second job. So let's dive in.
So that brings us to the big question for today. We've got this number called sequence in every transaction. On the surface, it's just a number. But what can it really do? Well, the answer is a whole lot more interesting than you'd probably guess.
All right, here's how we're going to break it all down. First, we'll look at its hidden past. Then, we'll see how it became this crucial signal for replacing transactions. After that, we'll uncover its second life as a time lock. We'll explore how it measures time, and then, for the grand finale, we'll reveal the surprising link that ties these two jobs together.
Okay, let's start at the very beginning. This sequence field wasn't always the multi-talented number we know today. It actually had a completely different and, well, ultimately abandoned purpose.
Yeah, way back in Bitcoin's early days, the idea was that you could use the sequence number to update or replace the transaction you'd already sent out. But this opened up a can of worms, potential for abuse, so the whole feature got disabled. And just like that, the sequence number was unemployed. It had no real job to do.
But this little number wasn't going to stay on the sidelines for long. A new problem started cropping up. Transactions getting stuck because the fees were too low. And guess what? The sequence number was about to get a brand new lease on life.
The solution was a system that you've probably heard of called opt-in replaced by fee, or just RBF. The concept is actually pretty simple. If your transaction is taking forever, you can just create a new version of it, but this time you offer a higher fee to the miners. It's their incentive to grab your transaction and process it first.
So how does this actually work in practice? Imagine you send transaction A, but you cheaped out on the fee, so it gets stuck. No problem. You can broadcast transaction B. It's basically the same payment, just with a more attractive fee. And the key, the magic, is in step 4. Use the sequence number to signal to the entire network. Hey, this one is replaceable. Miners see that signal, see the higher fee, and they'll drop your old transaction for the new one.
So here is the nitty-gritty of how you send that signal. It's all laid out in something called Bitcoin Improvement Proposal 125. All you have to do is set the sequence number to any value that's less than its maximum minus 1. It's a really explicit opt-in choice. If you don't set this value, your transaction just can't be replaced this way. Period. Now, RBF wasn't a hit with everyone right away. Some businesses worried about accepting payments that could just be reversed. So a compromise was made. By using the sequence field as a clear, deliberate signal, anyone who didn't like RBF could just choose to ignore unconfirmed transactions with that signal on. They could just wait for it to be set in stone in a block. Okay, so the sequence number got a pretty cool new job as a fee replacement signal, but that's only half the story. Believe it or not, it was about to get a second, completely different and super powerful role.
Probably the easiest way to wrap your head around this second job is to think of a post-dated check. You write a check today, but you put a future date on it so it can't be cashed until then. The sequence number can do exactly that with Bitcoin. It can lock up funds until a certain amount of time has passed.
The technical name for this is a relative time lock, and it's a rule that's enforced by the whole network. Now, the key word here is relative. The timer doesn't start ticking from a specific calendar date. Instead, it starts relative to when the Bitcoin being spent was last confirmed in a block. So you could, for example, lock funds for, say, 100 blocks after you received them. So if it's a timer, how does it actually measure time? Well, it turns out it has 2 different ways of doing it. Let's take a quick look. So the sequence number can specify a time lock in one of 2 units. The default is super straightforward. It's just a number of blots. But if you flip a specific bit, a little type flag, the value is interpreted differently. It becomes a multiple of 512 seconds, which, by the way, is a pretty good approximation of the time between Bitcoin blocks. And this is where it gets really clever, seeing how it's all packed into this one number. This is the layout from another proposal, BIP 68. You can see there's a bit way at the top to just disable the time lock completely. Then there's that type flag bit we just talked about that switches between counting in blocks or seconds. And finally, those last 16 bits hold the actual time lock value itself. Pretty efficient. Now, because that time lock value only uses 16 bits of data, there is a limit to how far into the future you can set this lock. The maximum value you can set, whether you're using blocks or seconds, works out to be a little more than 1 year.
So let's recap. We've got two totally distinct features, right? Replacing transactions with higher fees and locking transactions for a future time. They seem completely separate. But what if I told you they're fundamentally connected in a way that's, well, it's just brilliant? Yeah, RBF and relative time locks aren't just two options that happen to share the same parking spot in the transaction data. The way they're designed means they are completely, intrinsically tied together.
And here it is. This is the big reveal. Anytime you use the sequence number to set a relative time lock on a transaction, you are also automatically activating the signal for opt-in replace by fee. You can't have one without the other. The two features are inseparable.
And this isn't some weird bug or an accident. It's totally by design. The source material makes it crystal clear. To use the time lock, you have to set the sequence number to a value that is, by definition, less than the RBF signaling threshold. So you get a 2-for-1 deal whether you wanted it or not.
And that's the story of the sequence number. It's a single field that went from being a disabled, forgotten feature to a powerful tool that does two critical jobs at the same time. It really makes you wonder, doesn't it? What other simple, overlooked features in Bitcoin's code might be holding the keys to its future? Thanks for joining me.